here. That's the screen we're using. Okay. Alrighty, so you can go ahead and start viewing. So again, like my but for whatever reason, Discord only lets me either use my camera right now or in the video. So I'm just having it in the video. So if you guys are watching this later, that's where you'll see me. But just so you know. Alrighty, so we are going to finish off our chapter on ethers by talking about the sulfur analogs of those, which are called, or rather, those would be called sulfides. But thiols are the sulfur equivalent of alcohols. So thiols generally follow the form of something RSH. So the SH group there is called a thiol, as opposed to an alcohol. Sometimes you'll see this called mercaptan. The word for that comes from 2 bits mercury capture. Because sulfur and mercury have very high affinity for each other, you'll see that like sulfur things are used to treat mercury poisoning as a result of this. You know, if you ever take inorganic chemistry, you know, if you're a chem major, which is doubtful because so many of you are in bio, but you'll see more about this relationship later on. Though I guess in bio you do talk about heavy metal poisoning, and you'll definitely see if you know, if you have untreated mercury in your system, it's going to mess with a lot of your amino acids and your proteins, the cysteines specifically. So you'll see them sometimes called mercaptans. This molecule here we could call ethane thiol, if we really wanted to, just like ethanol. Or we could say 1-thioethane. Either one will work. We probably don't even need that one there because we have only 2 carbons here, only 1 substituent, so it's okay. Or you might see this called ethyl mercaptan. One compound that you'll see a lot in biology, if you do any sort of kind of protein work, if you ever do like a Western blot or anything like that, you're going to see this guy where they call it beta-mercaptoethanol. And this is one of the stinkiest things I've ever smelled. It's awful. It is absolutely disgusting, but it's super useful in analyzing proteins. And so this is a very, very common thiol that you'll encounter in biology if you do any sort of lab stuff. If any of you go into, you know, any sort of biological research, you'll be using beta-mercaptoethanol a lot, which is abbreviated BME. Yay. So, cool. Examples of thiols. So there we go. We're going to see that thiols are more acidic than alcohols because sulfur is a larger atom, right? We see that if we compare the pKa's of these guys, this one's around 10, this one's around 15 or so in water. The reason that sulfur is a much better, rather the hydrogen on the sulfur is much more acidic is because the sulfur is bigger than the oxygen is. It can hold the negative charge better. It's a little bit more polarizable. So we see that those are better acids. So just some, you know, things that you've probably already seen before. We're going to see as a result is not a great base, but it's still a good nucleophile. So it's actually a better nucleophile to use if you want to do some sort of substitution reaction on an alkyl halide or something, because it's not going to be basic. So the risk you run with, say, something like this, if you take this guy plus sodium methoxide, for example, you might get some elimination products as well as your substitution products. So you might get a combination of the elimination product plus your substitution product. Because the ethoxide ion is basic. It's a pretty good base. So you run the risk of having multiple products there. But with the sulfur analog, the sulfide there, you don't run that risk. So if you do the same thing with the sulfide, you're going to pretty much only get the substitution product there. So you're not going to run the risk of elimination. So it's a good thing. So elimination is less likely because it's not as basic. So just keep that in mind. Let's see, what other fun stuff can we do with thiols? So they can be nucleophiles. You can do your SN2 reactions. You can do whatever you want to do with your nucleophiles. You can use them with sulfur. It's great, and it's especially good because it's not basic, so you'll end up having something that's more nucleophilic in nature, and so you'll have fewer side products. You'll have cleaner reactions, and that's always a good thing. One special thing that thiols do, if you give them some sort of oxidizing agent, oops, I lost a sulfur, you can form disulfides. So you can form a disulfide by using some sort of oxidizing agent. For example, if we were to do this with, let's say, we used basic bromine, those sets of things will be oxidizing. If we go ahead and do this, our first step here, with you guys, I'm sorry, I forget, do I normally do mechanisms like vertically, or do I do them like horizontally? Do I do it like this with you guys, or do I go down first? I can't remember.
Down first.
Down first, okay, cool. I'll just be consistent with that since that's apparently what I do. So, okay. So, we're going to see, we're going to end up with our product at the end here, but we'll go through the mechanism of how this process works. So, purpose of putting a base in here, we are going to go ahead and deprotonate our thiol. So, let's go ahead and, oh dear, let me go ahead and fix this, make it a little easier on ourselves. There we go. Okay, here we go. Doing this, we'll end up with our sulfide ion, which now can go ahead and attack our dear friend bromine. These lone pairs kill me, but we must draw them. Okay. So we're going to go ahead and brominate now our sulfur. Now that sulfur has a leaving group on it, we lose our other bromide ion. That's going off into nowhere. And so, now we can go ahead and take a second, let's just say it's deprotonated already. Same thing with the NaOH, it'll just go and do that. Gonna come around here, attack our sulfur, kick out the bromine. And, well, I'm totally way far down here, but lo and behold, you get your product. You lose another bromide ion, and there you have it. So you essentially will kind of deprotonate your sulfur. You will then activate it by putting on a leaving group, and then it's going to go ahead and be attacked by another sulfide ion, leading you to the product of choice. With our lone pairs, because we're good chemists, we're going to put them there. And so you can oxidize it this way. This is just one example, but there are many different oxidizing agents you can use to get your thiol to work this way. And of course, this is a very important biological reaction. You have enzymes to do this instead. You know that in your proteins, you have amino acid cysteine in there, which can form these disulfide bridges between various parts of your proteins to lock things in place. But you'll deal with that in biology. We don't have to worry about that here. So, good. Lucky us. So, that's how you can make a disulfide. You oxidize it, essentially. You oxidize some thiols. You can also then say, okay, you know what, I don't want you anymore. You can throw in a reducing agent, such as HCl and zinc, and you'll end up getting your thiol back out again. What's interesting about this is that this bond here is about half as strong as essentially most other covalent bonds. So it's kind of relatively easy to put on and break because it's not so strong. So that's why in biology we use it, because we can say, all right, I'm going to link two sides of this protein together using this disulfide linkage. And, okay, I'm going to go ahead and break this down now because I feel like it. I'm breaking this protein down. It'll be easier to do that than to break a regular covalent bond. This is also super useful, although it's not as common nowadays. If you were to go to the hair salon in the 70s and get what's called a permanent, that's when you either take your hair, if you have straight hair, you can make it curly, or if you have curly hair, you can make it straight. By taking advantage of this relatively weak disulfide bond. So the curls in hair arise because of these disulfide linkages. And so through using chemistry, you can break them all without breaking all the other chemical bonds in your hair, although there certainly is some damage when you do this. You can therefore either straighten it or force it into a curled shape, and then reoxidize these back to disulfides, and now your hair is locked in whatever shape you want it to be in. So first you would break all these disulfides, then put your hair in whatever way you want. If you want it curled, you would curl it and then reoxidize. Or if you want it straightened, you would straighten it and then reoxidize. And you can end up with a perm that way. Do people still get perms? I don't feel like this is a thing anymore, but that used to be something. So there's your history lesson for today. Cool. Alright, what else can we do with these pesky things? Okay, here we go. Another one. We can actually talk about Thio Ethers. If we were to put this guy with, say, some base and some electrophile, we can get essentially the same thing as our Williamson. Remember with Williamson we did an alcohol and an alkyl halide with a base, and we got the ether out. We can do the same thing with thiol. This is called a Thio Ether. So thiol, just like alcohol, can turn into an ether with an alkyl halide. You in fact could even use a nicer base. You don't even need sodium hydride. You can use something like sodium hydroxide for this. So because the thiol is more acidic, you can use a gentler base. So if you wanted, you could use NaOH instead. A little bit safer. Though again, no, I'm not an artist. Leave me alone. Okay. And you can end up with your Thio Ether this way. So really the same process. You deprotonate, attack your alkyl halide, and there you have it. Very exciting. So same mechanism as Williamson. We just use a sulfur instead of an oxygen here. And interestingly, though, while ethers are boring, that is to say unreactive, Thio Ethers are still chemically useful. And so, for example, you can take a Thio Ether like this and put it with, say, here, well, I'm just going to actually make this a little bit more generic. You can put this with another equivalent of some electrophile. So again, while ethers are kind of boring and neutral, all you can do is break them, thiols we're going to see we can do interesting things with. We can actually see that this thiol, it's bigger, it's still nucleophilic, even as a thio ether. What you can do is make something that has a charge on it. Oops. Because sulfur, again, because it's bigger, can more likely, or it's more suited to accommodate charges. So that was the reason, again, why the sulfur is a little bit better for to be an acid, is because the S- ion is a little bit more stable than the O- ion. And so it's the same thing. The sulfur is better at accommodating a positive charge because it's not only bigger, but it's also less electronegative than oxygen is. So it's a little bit better for sulfur to be positive. And what's great about this is now this is a potent alkylating agent. And an alkylating agent means you can put it with something that's nucleophilic and stick a methyl. I mean, in this case, it's a methyl. If I put ethyl bromide in instead, we would have an ethyl group to put on somewhere. And so we can say, let's go ahead and put in some sort of nucleophile. I'm going to just copy it down here. Here's our nucleophile. Oh, that's a plus. Okay, so nucleophile is going to come in and attack our sulfur. I'm sorry, it's going to attack the methyl group there, which is withdrawing. It's going to kind of have a partial positive because it's right next to the big positive. And so our nucleophile is then going to attack that methyl. We're going to regenerate our sulfur species. The sulfur is not going to be attacked. Anybody want to guess why? Why is the nucleophile going to go after that methyl instead? Any guesses?
Less electron negative, I guess.
Not necessarily. So, the reason is not electronic. Maybe that'll be a little hint there.
It has a H group.
It has an H group. Well, so let's say these are. I'm gonna make it real obvious. I'm gonna put some T-butyls on this dude.
Steric?
Yes. So that sulfur would be tertiary, right? Depending on what we have on it. Indeed, if we did have H's on the sulfur, yeah, the sulfur probably would be attacked. But we'll say the R groups are not H's. And so that sulfur there, once it's tertiary like that, is most likely not going to be able to be attacked by a nucleophile. So while carbons that are positively charged are planar, they're sp2 hybridized, most other heteroatoms, when they are positively charged, still are sp3. So it's not flat. And so as a result, you've got these bulky things kind of blocking the sulfur. And remember that SN2 reactions don't work on tertiary substrates. So that's why we're going to go for that methyl instead. But look, now what we've done is we can say, aha, now I've put a methyl group on whatever my nucleophile was. If it was an alcohol, I've made an ether now. Or if it was a Grignard reagent, I've thrown an extra carbon onto something. It's good. So this is, you've essentially made a very nice electrophile here. So if you want to make a carbon into an electrophile, you can do something like this with sulfur. So now we have this kind of bit here being a good electrophile. So we can add that on to a nucleophile. We saw previously with the Grignard reagents, remember when you have your magnesium bromine thing on your carbon, that made it into a carbon nucleophile. By having it attached to a positive sulfur, you make a nice electrophile. So already kind of in this first chapter here, we're talking about making carbon into nucleophiles and electrophiles. Carbon that's not an alkene, for example. We saw that, with alkenes we can do additions and whatever we wanted with them, but these are now just regular old carbons. So there we go. We're building on stuff. Okay, so, and then we're going to end up with our methylated nucleophile. We would deprotonate it or whatever. We would probably make it more stable somehow, and then do whatever we need to do with it. So, just more cool things you can do with sulfur. Speaking of which, let's do some more. We have a couple more. Because sulfur can kind of go expanded octet on us, with oxygen, with regular ethers, we're stuck in period 2, can't go more than 4 electron domains. But sulfur has no such problems. We can go ahead and oxidize our sulfur if we want to. This is called a sulfoxide. This is a Thio ether. This is a sulfoxide now. So if you oxidize your sulfur, you can stick an oxygen onto it. If you wanted to keep oxidizing it, oh, and shame on me, now I've gone to the side. Oh well. You can go crazy and oxidize it some more. This poor sulfur. This is called a sulfone. Those have important synthetic applications, but I don't think we do them in this class. The Julia sulfone coupling. I'll have to check. I don't remember if we cover that reaction or not. But you can oxidize your sulfur because it can go expanded octet, right? It's happy to do so. And what's interesting is while we typically draw these as double bonds, in real life, these sulfoxides and sulfones actually have more single bond character than double bond character. And so that's that'll be important when we... Actually, you guys already talked about the Swern oxidation, didn't you? When you're talking about alcohols? Probably. You'll see that if we kind of just resonate this guy, we see this is actually closer to reality. Even though we typically draw them as double bonds because we are taught, Lewis structures, we want to minimize formal charges. Formal charges are bad. The reality of the bond length and the polarity of this does indicate that it's closer to having full charges than it is to having partial charges. So that's important because in your Swern oxidation, you end up having DMSO, right? Dimethyl sulfoxide, as one of your reagents, and you have it being attacked by chlorine, or rather a chloride ion, later on. So the reason for that is because the sulfur has a pretty much a positive charge on it. And so that oxygen being smaller, it's not going to prevent it from being attacked, like those T-butyls would have been earlier. Anyways, same thing with the sulfone. In reality, our sulfone more looks like having a 2+ charge on it. And so just understand that. So these behave more like single bonds than double bonds do. Then they behave like double bonds. So the evidence does suggest this. So it's just some more cool things about sulfur. Because sulfur is so polarizable, we can go ahead and mess with it all we want. Poor sulfur. But that's okay. So, just kind of more, what things to do with sulfur. Just like with oxygen when we were oxidizing it, remember when you took your alcohols, you could oxidize them into, say if it was a primary alcohol, you could oxidize it to an aldehyde or to a carboxylic acid, depending on what oxidation agent you used. Same thing with these. If you put in a really strong oxidizing agent, you'll probably get the sulfone, but you have milder ones, you can get the sulfoxide. So these, I don't think we're gonna look at the sulfoxide and sulfone as functional groups in this class, so we don't have to worry about which reagents those are. If we do, I don't think we're going to talk about those, but if we do encounter them in the future, I'll talk about which oxidizing agents you can use to go from one to another, or you can go crazy and go all the way to the sulfone. So, but right now, let's not worry about that. And let's see. Oh, one other place we've seen sulfur before. Do you remember our dear friend this reaction, perhaps? We put ozone with an alkene. Do you remember this reaction, perhaps what happens in this? You have to put a sulfur compound here, DMS, dimethyl sulfide. Perhaps this might be familiar? Here, let's make that a little bit clearer. Do you remember this reaction? Oxidative cleavage of alkenes, or ozonolysis? Clearly not. Very good. Just notice here we have 3 oxygens in this intermediate here. Right? But in our products we only have 2 oxygens. The reason we need the DMS in there is because it's going to help by kind of sacrificing itself to become a sulfoxide. It's going to take that extra oxygen as a reducing agent. So that's kind of the last little bit you've seen here. Your dimethyl sulfide as a reducing agent. Did you even talk about alkenes last semester? Apparently not. You didn't cover tosylation, or you forgot all about tosylation. You forgot all about your alkene reactions. This is going great. Does this at least ring some sort of bell? Anything at all?
Something.
Sounds familiar.
Sounds familiar. Good. You've heard the word before. Perfect.
Yep.
Okay. Well, just remember with the 15 things we can do with alkenes, that's one of them. And that's just one example where we did use some of the chemistry of the sulfur there as a reducing agent to kind of help that process out. So that we do end up with our mild oxidative cleavage of our alkene. Alrighty. So, do we have any questions on these thiols? Or on the sulfur, or on any of the kind of ether or epoxide stuff we've talked about so far in this course. So, what I want you to know, these are the important questions, right? With this, I would say this is probably a pretty important part right here. I'll put a little green star by it. This is an important reaction to know. I don't particularly need you to, this is something from 105. I'm not going to test you on this, right? This is something that you have already dumped out of your brain. However, it might come back on the final, because that's unfortunately cumulative. But I don't need you to focus on this right now. So I would focus on this one. This is an important reaction here, using a sulfur as an alkylating agent, taking advantage of the nucleophilicity of sulfur. I mean, I guess this is important, but it's really the same thing as for Williamson. This would be important, reducing a disulfide back into thiols, and then oxidizing a thiol back into a disulfide. This is one mechanism for an example. I don't need you to focus on this one. I'm happy if you understand this top line here. 2 thiols plus an oxidizing agent, you get your disulfide. And this little bit here. Okay, I would say those are kind of the important bits. So here, I'll be good. I will hover over them for a second. So if nothing else, if you don't pay attention to anything else about these thiols, learn these 4 or 5 things. These are the most important, I would say. So I get OChem. We have a ton of information here. Thankfully, this semester is a little bit easier than 105 is. Unless you've completely forgotten 105, in which case it'll be twice as hard. But that's okay. Alright, so these two, definitely get those. Definitely about this reduction. This is just any sort of reducing agent. If you remember back to 102, you talked about, electric potential and all that stuff. And you talked about electrochemistry. You can use anything that would reduce a disulfide. That's one of the common ones that's on your table of common potentials, reduction potentials. This one, same thing as the alcohol version, but you use a thiol to make a Thio ether instead of a ether. Alright, and then you can take a Thio ether, also called a sulfide, and you can go ahead and make an alkylating agent with it by treating it with some alkyl halide. Okay, so a little bit better of an electrophile than your alkyl halide was, so cool. Yep, there we go. Alrighty. Shall we move on to our next topic? We're going to talk about conjugated systems now. Alrighty, so, conjugation. Conjugation is when we have something like this. When you have alternating double and single bonds within a molecule, that's called a conjugated system. So, when we're talking about having multiple double bonds within a molecule, there are ways we can describe them. This arrangement would be, I'll just say that these guys are conjugated. They are alternating double and single bonds. We can have them like this. These are called isolated because there are more than one carbon in between them. And so we're going to see here they're not right next to each other. These now have extra carbons in between. They're called isolated. And then you can have them, in fact, on top of each other. How many carbons do we have here? 4 or 5? 1, 2, 3, 1, 2, 3, 4, 5. There we go. These are called cumulated double bonds, also called allenes. And so, we can see all of these. Allenes are less common. but they exist. Those are cumulated double bonds. But we're going to be focusing mostly on this top one in this section, conjugated double bonds. Because we're going to see that there's actually a stabilizing effect when you have conjugated double bonds due to molecular orbitals, our favorite thing that we've also probably forgotten from 101. So we'll have to go over that again. But conjugated double bonds are very useful. These often produce a lot of the colors that we that are present in dyes and organic compounds that are colorful. It's often because of conjugation. So by having all of these things, we're going to talk about where those come from, and I think you're going to talk about UV visible spectroscopy in the lab. I hope so. Otherwise, I have to take the time to do it. But I'll see if Chalmers will cover it. But I think that's a lab thing. So we'll see that, for example, how bleaches work. Bleaches don't actually destroy chemicals. Well, they do, but their kind of most useful purpose for us when you put bleach in something to get rid of a stain, what you're doing is that stain actually has conjugation in it. It's got conjugated double bonds, and what you're doing is breaking that conjugation by throwing the bleach at it. And so you're not actually getting rid of your stain, you're just making your stain no longer visible in the visible light spectrum. So, just so you know, so bleach people have been lying to you. They don't actually get rid of stains, they just cover them up. So, hooray. Another fun lesson for the day. Alrighty. Let's talk about conjugated systems. In all of these, I've put them as carbons, but we can totally have other things in here too. This would be conjugated. And this is in fact called an enone. It's an alkene ketone. These are all alkenes. Alkene. And those would be called aldenes, but those are a special case. We're not even going to talk about cumulated ones in this course, so we're cool. So yeah, you can have it with other things. You can have, it doesn't have to be two. You can have as many double bonds as you want. As long as they're all alternating, they form a conjugated system. So, doesn't matter how many you have. As long as you have them alternating with single bonds, you're good. And so we're going to talk about kind of what makes these special. But first things first, we'll talk about how to make them. So, how do we make conjugated alkenes? First thing we can do, we can take an allylic alkyl halide, throw in a nice bulky base, bulky base T-butoxide. So remember T-butoxide, non-nucleophilic base. So just like with the sulfur that was a non-basic nucleophile, this is the opposite. Now we have a non-nucleophilic base. So it's just too big. That's not how you spell that at all, is it? Non-nucleophilic. There we go. Just going to come in and you're going to get the elimination product. And you end up getting this. So you have no substitution reaction happening here because you're going to have a non-nucleophilic base. So you're going to get your conjugated thing out here. You're going to end up pulling this hydrogen off, and you're going to end up making your alkene. Ooh. Kicks out your leaving group, and poof, there you go. So elimination only. This is, in this case, I've put it as an E2 type of thing, where we are having our anti-periplanar fun good stuff. Again, hopefully words that are somewhere in the back of your brain there. This could go E1 as well. It just depends on your reaction conditions. I've drawn it as E2, but either way will work. So either way, you'll end up getting your happy alkene here. So that's one way to do it. And hopefully we'll remember how to make an allylic alkyl halide. I'm sure we've forgotten. If we have this. Do you remember this compound? Will selectively brominate an allylic position? Probably not. Okay, here we go. This guy familiar at all? You need light, by the way, to make this happen. I guess you've completely forgotten this one too, but just...
Yeah.
Yep, of course. Okay, so just remember that's how you can make one. So if you have a double bonded system, you throw in this compound N-bromosuccinimide with some UV light, and you'll go through some radical stuff, and poof, now you have an allylic alkyl halide, which now we can say, okay, we're going to go nuts and kick it off and get our double alkene here, our in this case butadiene, our conjugated system. Okay, anyways, we can also take the dibromide, throw in excess of your T-butoxide, and we'll get the same thing. So whatever you've got, lots of ways to do it through elimination pathways. We're going to see that these things are nice and stable, so they are happy to form. So throw in excess T-butoxide, you go through multiple eliminations, and you end up with your conjugated system here. So that's how that's gonna play out. Okay, so that's how you can make them. As long as you have these vicinal things, you can make it happen. Again, I've drawn these in simple cases where we have 4 carbons, but go ahead, throw them on more complex molecules. Same thing is going to happen here, so we're good. All right, let's talk about some properties then. All right, so if we're comparing these two molecules, butadiene and butane, technically 1,3-butadiene, I'll be correct. All carbons here are sp2 hybridized in this molecule here. Everything in this one is sp3 hybridized, right? No double bonds in our rightmost molecule. I have some numbers for us here. It's interesting to note, while these are both carbon-carbon single bonds, they do have different lengths. The one with our double-bonded system is actually a little bit shorter. 5 picometers shorter. Not very much. Tiny amount. But even though they're both carbon-carbon single bonds here, we can talk about that with the hybridization effect. That's one way to describe it. Remember that an sp3 orbital looks kind of like that. Oh gosh, this is going to be so hard to, like, kind of do. This is an sp2 orbital. Look at how... I'm such a good artist, guys. They look identical, right? Suffice it to say, this has less S character, right? And so it is, therefore, more P, which makes it look a little bit longer. So it's elongated. And this one has a little bit more S character. Oops. So it's a little bit shorter. So that's one way to describe this. We can say, well, it's just the orbitals that are involved here. We have shorter orbitals, so therefore our bonds are going to be shorter. We'll talk about this idea a little bit more when we talk about molecular orbitals. Another reason why that bond in the conjugated system is a little bit shorter than we would perhaps expect. So one explanation is just these orbitals that we have here. So just things to remember. This, of course, by the way, the top or left molecule is planar, right? It's all sp2. The other one is tetrahedral all over the place. So there's more things to think about there. If we are comparing alkenes, what's interesting to note is that having a conjugated system is actually going to be more stable than having just isolated double bonds. If we were to take two of these molecules and hydrogenate them, versus, we need two H2s there, versus the conjugated system, if we wanted to hydrogenate these, if we wanted to make them into our butane, we're going to see that even though we're doing effectively the same thing here, we see that the conjugated system is actually already a little bit lower in energy. It takes less energy for it to go into the completely saturated carbon, or alkane, than it would if we had just isolated double bonds. And so that tells us that conjugation provides about 15 kilojoules of what's called stabilization energy. So it's just a factor here that having these put together provides a little bit of stability to our molecule. Even though we're kind of giving it more energy, we might think, by giving it more reactive sites. Like, aha, now we have two double bonds, well now it should be twice as reactive, right? Indeed not, it seems. So having it conjugated actually makes it stabler, less reactive, than it would if we were to just have two double bonds that were separated from each other. So just some cool little bits here. So we do have a bit of stabilization happening with these.
That was a 2.
What two? In front of the hydrogens?
Yeah.
Or this thing over here? Yeah, that's a 2.
Oh.
Just because we're going to need two double bonds to make this happen. We could even say instead, here, we'll do it this way. Ta-da! So isolated double bonds, if we were to take essentially the same molecule but have those as isolated double bonds, should take about, I mean, these numbers might not be exactly accurate, but we're still looking at about 15 kilojoules lower in energy for having them conjugated than it would be otherwise. Okay? Sorry, sometimes my writing's not so great. Okay. Cool. Let's talk about conformational analysis now. Do you remember all this fun stuff about the Newman projections and the gauche and the sin eclipsed and whatever. All that fun stuff. Don't worry, we don't have to do with that here. We just have a few things to look at. So, that single bond in between conjugated bonds like this C2, C3 bond is free to rotate, right? It's not part of the double bond. That's a single bond. We can rotate around it. These things do indeed rotate. These are rotamers of each other. I guess I've given it away by putting my equilibrium arrow there, but presumably you can see one of those is better than the other. Better in terms of its lower energy, right? We know that having them trans to each other is going to be lower energy because we're not going to have things sticking into each other. These are bonking each other a little bit, whereas here we have everything well, we'll just throw that there. Okay, see, we've got a little bit of steric repulsion here, even if they're just hydrogens. We're going to see that this form is about 2% at room temperature. That's about 98%. We have words for these. So while there's free rotation, if we were to just take a snapshot at whichever particular rotational isomer it's in, we call this one S-cis, and this one S-trans. So, cis and trans, just like before, we have cis meaning same side, trans meaning opposite sides. So, along that single bond, which is free to rotate, our double bonds cannot rotate, but our single bonds can. Along that bond, as we rotate these, our diene can kind of adopt two forms. It can be the cis form, the S-cis form, or the S-trans form. And again, it's rotating constantly. At any given time, about 2% are in the S-cis conformation, and about 98% in the S-trans conformation, again, just due to steric reasons. Our trans is sterically more favorable because our groups are pointing away from each other, so we don't have any nasty interactions. For some numbers, if we were to think about how these might go between each other, I have a reaction coordinate diagram here. So between those two, if we want to rotate them, we do have a bit of an energy barrier to overcome. That is also about 15 kilojoules. So it's the same amount of energy as we get for making a conjugated system is the energy it takes to rotate that particular molecule. And just so we know, the difference here between the two forms is about 12 kilojoules or so. So we're looking at kilojoules per mole, right, for all of these. In order to rotate, there is a sizable energy barrier that we must overcome, but we do get out of that a nice little energy reprieve at the end. Just so the point of this, if you're at lower temperatures, it's going to be less likely that you're going to be able to rotate things. We're going to see that'll be important when we talk about reactions of dienes later on, that we want some temperature in there that we're going to need. So later on, some energy, or let's say energy, is required to rotate between these. So if we want to rotate from the trans to the cis, we have to go up 27 kilojoules per mole to do it. And then, the 15, that's just the activation energy, right? So, we'll end up a little bit not 27 kilojoules higher, but we still got to put energy in. That's the point. Put energy in to get them to rotate. We're going to see later in a very important reaction that you will come to love. It will be your best friend. You should be afraid when I say that. You have to have the cis conformation. So we'll see there that we're going to have to put some temperature into things in order to get them to get in the proper position so that they can react happily together later on. So just keep that in mind as we go through this. Alrighty. So, who remembers molecular orbital theory? No one, I expect. From 101. It's been at least 2 semesters now since you've taken 101. But suffice it to say, if we're looking at a single double bond, kind of a weird way to say a single double bond, but let's say we're looking at this molecule right here, ethene. Do you perhaps remember that molecular orbitals, hopefully this shape is familiar to you, you'll end up populating your lowest orbitals. We're going to have, in this case, pi and pi star, perhaps. Bonding and anti-bonding orbitals. Hopefully we remember these things. Our electrons are going to want to go into the lowest energy orbitals. They form these molecular orbitals because they're going to be energetically favorable. As we can see, as energy goes up on the side here, we're coming lower in energy by putting our p electrons into a pi bonding orbital. If we had more electrons, we'd have to put some in anti-bonding, but thankfully we don't have to do that because we only have 1 pi electron that we deal with double bonds. So how these might look, I'm going to just kind of draw our just carbon there. If we're looking at the bonding orbital, it kind of looks like this, where we have overlap between the two. And if we look at the anti-bonding, we have the opposite problem happening. We have a node here. And so you remember that p orbitals, okay, I have to do them in different colors because we're going to see that this is going to be important. P orbitals, when they overlap, or they have kind of 2 ways of mixing, right? We can have them mix where we have them right next to each other, the same colors. In this case, that's what gives us. Let me move that over. Oh, she's just snoring down there. That's what that sound is. Okay. If we kind of arrange them this way, that leads to this sort of orientation where they're overlapping. Oh, I've put them upside down, haven't I? Ugh, how annoying. Okay. Can I rotate this? No, not really. Fine, I'll redraw it. Okay, let's try that again. Alright, so if we have them next to each other with their kind of same lobes in the same direction, we end up with this kind of nice, happy overlap between them. That's our pi bonding orbital. Here we have our pi star bonding orbital because these two have come together where things are the opposite way. So these have come together and have mixed to form this kind of terrible anti-bonding orbital where we have the same portions of the orbitals not overlapping, but they're actually separated from each other by a node. So remember, the node is something you can't pass between. So our electrons here are nice and happy and are able to kind of move between the orbitals on the left side. On the right side, they're completely isolated from each other. And so there's no bonding that's happening there. It's anti-bonding. So, not so great. So, but that's what they look like. And we can take this now to a more complex example. If we want to look at this molecule, the 1,3-butadiene, we now have, we've got 4 p orbitals in this molecule, right? These are all sp2, meaning they have 1 p orbital left. So we have 4 p orbitals with 1 electron each. So all of these all these p orbitals have 1 electron, so we've got 4 p electrons all. Let me try that sentence again. We have 4 p electrons total. There we go, that's what I'm trying to say. And if we were to draw the molecular orbitals from them, in the previous problem, we had 2 molecular orbitals because we had 2 electrons, right? So with 4 electrons, 4 orbitals, we're going to end up with 4 molecular orbitals as well. We end up with 4 molecular orbitals. And so, again, those 4 p orbitals will combine together. We're going to end up making 4 different ways of arranging these. And like before, we're going to see that our lowest energy state is going to be when all of them align with each other. So we have 0 nodes. So the electrons are completely free to traverse the entire molecule. So they can go crazy. They can go all over. So they're all kind of happily integrated together. You might see this kind of, written then as this kind of blob, because all of these completely overlap, and we have this sort of nice arrangement of them. So that's our lowest energy state. And we're going to have 2 electrons there. So 2 electrons are going to go into that state. Kind of drawn it on my lines, but oh well. We're going to have 2 electrons that go there. We're going to end up having 2 that go here as well. Our next lowest state is going to have 1 node. We always increase our number of nodes per energy level. So as we go forward, we're going to have 2 nodes up here and 3 nodes at the top. Nodes are areas that are forbidden for electrons to cross. So electrons cannot move past a node. If we have 1 node in our molecule, that means we have 1 area where those will kind of flip over. So we've got now 1 node in between these, in our molecular orbital here. So in reality, goodness gracious. Okay, let me erase this. I need more room. We're going to end up having this sort of idea. So we've got blobs and blobs over here. We have a node there, what that might look like. If we want to look at the next orbital, we're going to have 2 nodes, and what that is going to look like, we need 2 areas where they flip over in this. So that might look something like this. We've got 2 nodes now. And so if we're looking at these together, although we don't have any electrons in this particular orbital, it's still very important that we understand how to draw it. What that might look like. We have single things up top, blob on the bottom. Electrons can only move within their blobs. So the two electrons in the middle are able to kind of be happy and interact with each other, but the ones on the sides are kind of isolated, and they're very sad. And our last case, which has 3 nodes, is going to have completely alternating p orbitals. We have 3 nodes there, and that's going to end up just looking exactly the same. Oops. No. I don't know, discard this. Okay, there we go. Oh my gosh, so many colors. Okay. Trust me, this will come into usefulness later on. So, we have 4 different orbitals, all with different degrees of orbital overlap. In the lowest energy there, all of the orbitals are overlapping together. Those 2 electrons are able to go wherever they want in the molecule. So they can hang around up at the top left or go to the bottom right, wherever they want to go. They're happy to go there. In the next case, the next higher energy up orbital, we have kind of them separated in half. So we have 2 electrons on one side, 2 electrons on the other side. And then we just keep going on more and more. What these might look like... Okay, time to erase this part too. What this might look like... Well, I've drawn it as trans, but this might, if we were to draw like bonds for this one, we might draw it like this, where we've got complete sharing of electrons throughout the entire molecule. What we see with this one is it looks like what we would normally draw a molecule. We have kind of one section where we have shared electrons on the left, and then we have one section of shared electrons on the right. And we typically will just draw those as a pair of double bonds, and that's the normal way we would describe this molecule, right? And we're going to see why that is later on. Our next case would be something like this, where we now have a double bond in the middle, but 2 radicals on the sides. So they're kind of just doing their thing. And then the last case, we have radicals everywhere. So those p electrons are completely separate from each other, and we've completely got no double bonds at all happening.
I have a stupid question.
Yes.
So what was the difference between the blue and green blobs?
So, how p orbitals work... P orbitals generally look like this, and we just typically draw them like this, right? We see that we sometimes talk about them as having like a positive end and a negative end together. The electrons in p orbitals kind of tend to like to be in one side or another. And in order to kind of put p orbitals together, we have to have the same type of like section of it overlapping. So if we want 2 p orbitals to be able to mix together, we want them to both be the kind of the same side of it. So if we want them to be able to kind of fuse together, they have to be the same. So doing it this way, you'll end up with now kind of our bigger, like happy shared one, where we have them like this. And this is all like mathematical statistics, fun, good stuff. Suffice it to say that for purposes of what we need to know here, is that we just want the same kind of portion of the node, the portion of the orbital on different orbitals, the same spot of it, to be able to interact together. And that's going to make things happy. I can probably find a video on YouTube or something that's going to explain it a little bit better than I can. And I can put that in Discord later for you guys. But, yeah, go ahead.
Oh, thank you.
Yeah, sure. So, things will cancel out otherwise. So they'll annihilate each other if we try and put them the other way. So positive and negative will kind of cancel each other out. So we want them to be additive. So anyway, so I do it with colors just because it's a little bit easier to see than positives and negatives and stuff. So, yeah. All right. What color haven't I used? Okay, let's see. Purple. These two orbitals in the middle, the one node and two node ones, are of special interest to us because those are the ones that are going to take part in reactions more often. Those lower energy electrons at the bottom there in the 0 node kind of molecular orbital, those ones are so happy they're not going to react. They're low energy, those aren't going to be taking place in reactions. However, these higher energy ones, the ones that look like the normal butadiene structure that we typically draw, this is what we call the highest occupied molecular orbital. And we call this one the lowest unoccupied molecular orbital. Let me write out those down here. Unfortunately, I just have no space, so I'm going to have to draw those down here. So your highest occupied molecular orbital, abbreviated HOMO, is going to be your highest energy electrons in the system. You also have the lowest unoccupied molecular orbital, which is called the LUMO, and that's going to be your I don't want to say lowest energy unoccupied orbital. Self-explanatory, hopefully. So that's kind of where we would put electrons. Accommodate has two M's, doesn't it? Additional electrons. Again, not as useful there, but we're going to see that talking about these two orbitals is going to be important for us when we talk about pericyclic reactions. We're going to see that we're going to need to overlap the HOMO of one orbital and the LUMO of another molecule, rather. So the HOMO of one molecule, the LUMO of another molecule, to get them to react together. And so we're going to see that it's important that we understand how to draw those. So understanding that these kind of blobs form will help us later on. But when we talk about addition reactions here, we'll see that that's the case. Or rather, we're going to kind of set these to the side and talk about them later. If we were to have, by the way, hexatriene 135, this molecule here, we always draw it as the HOMO, by the way. This is a kind of molecular drawing of what our highest occupied molecular orbitals would look like. We're going to see here we have, therefore, kind of two nodes in this. So if you want to cheat that way, that's great. We typically will draw the HOMO state of the molecule. We can tell that the lowest state, by the way, is going to be just completely all blobbed up. But if we want to draw the orbitals out, we can. Okay, let's do it. Do I have time? Not really, but we'll do it anyway. Hexatriene is going to have 6p orbitals. Which I can... Is that 6? Looks like it. We're going to see here... I've totally taken all the space. Okay. I'm going to just draw them without the individual dots. But we're going to go through the same thing. We're going to have 0 nodes, 1 node, 2 nodes, 3 nodes, 4 nodes, 5 nodes. We're going to see how these look. If we have 1 node, we're going to have 3 of our things on each side. Happy together. Here's my lovely blobs. If we have 2 nodes, those are going to be groups of 2 then. That is our normal view of hexatriene. We've got that blue blob up there, blue blob, 3 different blue blobs. I'm just choosing the blue blobs. I could have used the green blobs if I wanted, but we see that there are 2 nodes in this molecule. Those are those kind of separations. And as we keep on going, the next one we're going to need 4. So we're going to have blob, blob, kind of isolated section here. So we really have kind of something that might look like an alene here. Or no, I'm sorry, we're going to have the 2 double bonds in the middle and radicals on the end. So we see these are kind of the important, the most important orbitals in this molecule, the HOMO and LUMO. HOMO being on the 2-node section, the 3-node section being our LUMO. If we really wanted to draw the next ones, we could. 4 nodes. Let's see. If we draw 4 nodes, we're going to have now kind of 1 blob in the middle. And alternating 1, 2, 3, 4, 5. There we go. Blob. So we've got now 1 double bond kind of in the middle. And then at the very top, again, we just have everything alternating. 6. Okay. So, if we were to draw these, we'd see we just have dots everywhere. Looks like artwork. With this one, we have just 1 kind of double bond in the middle. If we were to draw these, we're going to see we have kind of happy sharing going on between all those. And then finally our lowest energy one is everything completely shared. So that's what those might look like. So again, typically we draw molecules as their highest occupied molecular orbital. So we're more comfortable that way. That's how we've been working. That's what that's going to look like. So it's going to be the same kind of pattern for all of these. If I gave you one with 4 double bonds, you'd have 8 orbitals to draw. You just keep increasing the number of nodes as you go through. So, like for example, here are the nodes. Every time we switch, we have a node. So in the bottom section here, we have no switching. All of the blues are on the top. All the greens are on the bottom. There's no switching going on, so there's no nodes. In the next one, we're going to switch halfway through. So we have 1 node right in the middle. We always want to kind of keep our double bonds kind of towards the middle as well. This because they're more stable that way. We already know that. If we have 5 nodes, that's every single place switches. So those behave more as radicals. Again, we don't really see things in this. Remember that this is energy, by the way. As we go up here, energy is going up. We do have something interesting that we can talk about. So for this molecule, we have 3 antibonding orbitals that are not filled, 3 bonding orbitals that are filled. And so we have the set of electrons that looks like that. If we were to give this some light, we could promote an electron up there. We could promote this electron to being up there. So we could totally do that if we want to. And that's going to be the basis for UV visible spectroscopy. So that energy difference is within the UV visible range of the spectrum. So by zapping something with a particular wavelength of light, we can promote electrons up to higher energy orbitals, typically from your LUMO to HOMO, or HOMO to LUMO. And so we can promote an electron that way. So if we get rid of this guy and now promote it up, we could have given it some energy, the photon for that energy. Remember that in these orbitals, energy gaps are quantized, so there's a specific amount of energy that's required to go from one orbital to the next. And so that energy would be equivalent to the color of the light that you're zapping this with. So that's why these things can be colorful. The more conjugation you have, the more of these orbitals you have, the closer they are in energy. The closer they are in energy, the lower the amount of energy you need to zap them to get them to absorb light. And therefore, the more likely we are to see them. Right? If you want, most molecules will absorb UV light, but if we want them to absorb visible light for us to be able to see them as colorful, you have to have them having closer and closer energy gaps to each other. So that just means more and more conjugation. So that's going to be done in the lab. Is where you'll talk about this, I hope. Because I don't want to. This is really a lab topic anyway, but that's kind of where that's going to come from. So, wow, what a lot we've done today. Lots of lovely drawings. I didn't do that badly this time. I'm usually much worse at the artistry of these orbitals, so hopefully that's not going to be terribly confusing there. I would expect you to be able to generate something like this, by the way. So either with the discrete kind of orbitals here or the overlapped ones on the left there, either way. This would be something I would expect you to be able to do for a given molecule. So just be aware of that. I'm sure you'll go over this more with Professor Charmas tomorrow, as you are having some extra time in lab to do so. On Monday, we're going to talk about We're going to talk about 1,2 and 1,4 additions to dienes. We're also going to talk about pericyclic reactions. So just, if you want to read ahead, we're going to be talking about these things on Monday. Mostly the Diels-Alder. But we'll see what else we get in terms of pericyclic reactions as we go on later on. So, we're going to see also kinetic versus thermodynamic control. Is that something you've talked about in 105? I've never taught 105 at GCC, so I don't know if that's covered there. Do you talk about kinetic products versus thermodynamic products? Maybe when you're talking about alkenes? Kinetic products are ones that come from their more stable intermediate, but thermodynamic products give you the more stable product.
I can't remember.
GCC for 8A, but it's the equivalent, but I don't know that GCC.
Okay. Very good.
Where it's on a graph.
Where it's on a graph. Okay, like the reaction coordinate diagrams? Like these sorts of things?
Yeah.
Yeah, okay. Yeah. Okay, so I'm glad it's somewhere in your brain. So yeah, we'll have that next time. We'll see the kinetic ones will have lower activation energies. Here, I'll even so you'll see that this might be your kinetic product, but your thermodynamic product will be the I'll have a higher energy gap, but it'll take you lower at the end. So that's the kind of difference you'll see there. So yeah. So good. I'm glad it's somewhere in the recesses of your brains. So, but we'll talk about that on Monday then. Alrighty. Just remember, I am gonna have my office hours be kind of set since this is a synchronous course. So Mondays 12:15 to 1:15, I am available for you guys for questions. If you want me to show up, just ping me, because I'm not gonna just hang out here all alone. I'll feel lonely. So what you'll do is you'll do this. Something like that, where I've typed in our general chat, so do something just like that, and that'll let me know that you want me to show up, and we'll come in Discord, and we can do whatever we need to do. So, yeah. So that's, remember, Mondays, 12:15 to 1:15. So that's going to be my office hours. But Professor Chalmers will also be doing tons of practice with you guys, so he probably has more office hours because he's obligated to, so I only have to have just one, so yeah. Cool. Alrighty. I'll see you guys next time then. Enjoy the rest of your day, enjoy your weekends. And we'll continue on with this lovely idea of conjugated systems next time. As usual, I'll put this on